Hello, and thank you for tuning in to my poster presentation at Cryobiology 2020. My name is Charles Andrew Elder, and I am an undergraduate student at the University of Louisville studying biology and psychology. I currently work for Dr. Michael Menz as a research assistant on his blood desiccation project. Millions of people have died due to the unavailability of packed red blood cells because they must be maintained at 4 degrees Celsius for only 35 to 42 days. This has driven scientists to search for ways to store red blood cells longer and at room temperature. My lab is interested in a process known as freeze drying. In the freeze drying process, red blood cell samples are frozen, and then the ice is lyophilized out of the solution, leaving the red blood cells as a powder. This red blood cell powder could be stored for years at room temperature and then rehydrated when needed. I am interested in optimizing this process. For red blood cells to be turned into powder, they must survive the freezing process without dying. Determining which compounds would be needed in solution to get the highest freeze-thaw recovery rate has been the goal of my project. In my experiments, red blood cells were frozen in liquid nitrogen at 50 million cells per milliliter in 1 ml samples. Different compound additions to a freezing solution composed of 200 millimolar trehalose and 20 millimolar HEPs at 7.1 pH were utilized during rapid freezing, and cell viability after freezing and thawing was estimated using a hematocytometer. The compounds tested included 60 millimolar sodium chloride, 60 millimolar sodium lactobionate, 3 millimolar magnesium chloride, 100 millimolar proline, and additional amounts of trehalose. To investigate the impact of water temperature during thawing, a reproducible spinning rate of 180 beats per minute was used to determine the best temperature to thaw samples at for red blood cell freezing viability. As you can see in Figure 1, 60 millimolar sodium lactobionate and 60 millimolar sodium chloride greatly increased the freeze-thaw viability of the red blood cells compared to the base buffer. Figure 2 shows that trehalose concentration is extremely important. Further optimization will be performed, but as of now, 400 millimolar trehalose is the best concentration to freeze red blood cells at, but 600 millimolar could cause them all to die. So you better make sure your concentrations are right. In Figure 3, we can see that by increasing the temperature at which thawing is performed, we can get higher cell viability than compared to thawing done at 40 degrees Celsius. It does seem like there is a max temperature at which thawing can be done at, which the heat from the water bath begins to kill the red blood cells. For my conclusion, salt-free buffer solutions are less effective in preventing cryo-injury to red blood cells than solutions supplemented with sodium chloride or sodium lactobionate. These solutions can greatly increase the viability of cells after freezing when used with trehalose. If trehalose is the only osmolalite, a concentration of 400 millimolar is most effective for cryopreservation, and rapid thawing of red blood cell samples at 55 degrees Celsius was most effective for reducing cryo-injury, potentially by preventing intracellular and extracellular recrystallization events. Some experiments that I will be performing in the future will help me answer questions like, can increasing salt concentration cause additional red blood cell protection for freezing and thawing? Are there better compounds to help with cryopreservation for red blood cells? And will increasing the sample size change the freeze-thaw variability of the cells? My acknowledgments go out to the National Science Foundation. Thank you for listening to my presentation, and I would love to answer any questions via email. Thank you.